papers on a variety of topics, which makes it even more interesting. So without further ado, I will let the speakers to start their talk. Please feel free to write your question in the chat, and I will monitor the chat frequently. So we will start with Oded, testing distributions of huge objects. So Oded, please share your slides.
Oh, thanks.
Sure.
Okay, so you hear me? Yeah. Can you hear me? Yeah. Or not? Yeah. Okay, thanks. So Dana was supposed to give the talk, but somehow we felt that it is more fun if I give it, although it's not clear why. So let's try. So the talk is about testing distribution of huge objects, and this title is supposed to reflect that it is this model that we are going to introduce and to initiate study of is a hybrid of two standard models, which I'll describe next. The slides are Dana's slides, so I don't know my way well in them, but we'll try our best. So the first model is a standard model of testing properties of strings or functions. The objects here are strings or functions, and a property is just a set of strings. And the algorithm has query access to the string, and so there, actually I should have started saying something else. When you talk about property testing, it's a type of sublinear-time algorithm, and you have to specify, actually, because it's sublinear, you have to specify two things. The first thing is, how are you going to access the objects that you are testing? And the second thing is, what is a distance measure? Because we'll have a notion of approximation, because we don't have, in sublinear time or in sublinear complexity, we don't have time to read the entire object. So we cannot make an exact verdict about it. So we can only make an approximate verdict, and an approximate verdict requires a measure of, and the measure will be how close is the object to the property. So if we go to the standard distribution, to the standard testing model of testing strings that I started to describe, the way you access an object, which is a string, is by querying its bits. And the distance measure, which you say, what is the distance of an object to the property, is just the relative Haike distance between the object and the closest object that has the property. So this is a standard testing property model. There is also a standard distribution testing model, which is vastly different. Here the objects are actually distributions, and the property is a set of distributions, and the access is that you get samples from the distribution, and you are obtaining a small number of samples, and the question is then what verdict you make, and what is the distance measure. And the distance measure in this case is a total variation distance between distributions. So this is a standard thing. And what I wanted to stress is that the complexity is sublinear. So in the case of testing strings, it means that it's smaller than the length of the string. In the case of testing distributions, the domain from which the elements is coming is large, and the complexity you want it to be smaller than that or compared to that. Anyhow, that's the things that you have in mind. And in all cases, it's randomized algorithms, so there is a probability of errors that I'm going to ignore. So as I said, the new model is a hybrid of both models. It's a model of testing properties of distributions, but the distributions have to be thought of as big strings or as very long strings, and therefore you're not able to read all of them. So as usual, I have to specify two things. First is my way of accessing the object, which is in this case a distribution on huge objects. And so the way I'm going to access the distribution is that I get samples from the distribution, but I'm not reading the entire sample. I'm just allowing a query access into the samples that I got. So this is a non-standard thing. So you see the hybrid of both models. The first that you are getting samples, and the second that you don't read the entire things that you get, but rather you only query inside it. So the picture is supposed to show it. The second thing is that what is your distance measure now? And the distance measure, I want it to be more refined than the total variation distance, because it has to reflect this notion that I'm not accessing the entire string. So the thing that is natural here is to say that if you move some probability mass from one string to another string, you don't pay a unit cost like you would in the total variation distance, but rather you pay a cost which is proportional to the relative Hamming distance between the two strings. So this is really the earth mover distance under the normalized Hamming distance. So this is really what the distance we are talking about. And there is a formal definition here, and I don't want to go into it. I just want to show that it is vastly different from total variation distance. Consider the following two distributions. One is uniform over strings that start with 0, and the other is uniform over strings that start with 1. In total variation distance, they are at distance 1, at maximal distance, because we're talking about distribution on disjoint supports. But in the earth mover distance, they are in very small distance, because it's enough really to change 1 bit in order to move the mass from these guys to these guys. Okay, so I think, and there is a name. So in order not to say all the time distribution over huge objects, and that's the name of our model, we call it the Doho model, and but I'll forget to pronounce it. Okay, so just some initial observations. The first one is that really this model is a generalized. It's not surprising, since it's a hybrid of the two standards models, you can really naturally or unnaturally embed or represent or think of the origin of the standard models as special cases of this model. And I'll not get into details. If you think about it for 2 minutes, you can see it. The second observation is that if you compare this model to the standard model, then the sample complexity of testing a property in this model may be smaller than the sample complexity of testing the same property in the standard model. And the reason is the distances here are smaller. Since distances here are smaller, you have to reject only things which are far from the, maybe I didn't even define what property testing is. So usually we want to distinguish elements which have the property from elements which are epsilon far from the property, where epsilon is a proximity parameter. So the issue is, it's a promise problem. So the question is, for what object do we have to give the right answer? So if an object is close according to one measure, but far according to the other measure, so when we work with the other measure, we have to reject. But when we work with the first measure, we may not need to reject because it's smaller than the proximity parameter. Okay, so the third observation is really a triviality, is that what we really want to study is not so much the sample complexity in the Doho model, which was the subject of the previous observation, but rather the query complexity in this model. And there is an obvious answer that the query complexity in this model is just the sample complexity in this model times the length of the strings. But of course, we are not interested in this idiotic case. So what we are interested is in the case that the query complexity is much smaller, or significantly smaller, if you want, than this project, than this product, than this obvious bound. And this is really the focus of this work, to initiate a study of which properties can be tested in such a complexity. So we have one result. We have several results, but we have one result in this direction. And the result in this direction is really a win in a way. It says that we can do it for some type of properties. So I want to describe what type of properties we can do it for. So the type of properties that we can do it for are properties of distributions that are closed under mapping. What is here?
The time.
Time. What about the time? I'm done. Or I should stop. Okay, so I'll just say, sorry, I'm totally off. So basically, I'll just state the theorem. The theorem says that if you consider properties that are closed under mappings, which means if something has a property and you take some mapping from the strings into other strings, then you get a new distribution on strings, and this distribution has to have the property also. So if the property has this feature, and properties which have this feature contain, for example, properties that have bounded support size or uniformity over some set, then you have the feature that the query complexity is really just the sample complexity in the standard model times some things that doesn't depend on the length of the string. So I'm sorry for going over time. I didn't notice.
Yeah.
Dana is helping, but the help came too late.
Yeah,
so I'm not thanking you. I'm asking for forgiveness.
No worries. It's all right. So I have one quick question. So in the model that you described, so the query complexity is basically the sum of the queries that we make to the samples. But for the same sum, we might actually be able to have different, trade-off between the number of samples we take and the number of queries we do per sample.
Right.
Does is there any preference for the? Basically, what I'm trying to ask is that if the total number of queries are the same, how do we measure? Like, do we have a special preferences for the algorithms that take lower samples?
Naturally, I would say that if all is equal, then we prefer less samples. So the sample complexity is definitely a measure that we consider. But the primary measure for us is query complexity. Of course, somebody can come and think differently. But what you're proposing is that there could be even a trade-off. I'm using slightly more queries, but I'm using vastly less samples. And should I prefer it or not? I think it depends on the application, and let's say the existence of such things. I don't know if an example of such a thing, but the existence of such thing is also a natural open problem, in my opinion.
Okay. There is one more question on the chat about which says, could you elaborate a bit about the choice of Earth mover distance? Why is that the natural metric?
It is hard to answer such questions. So basically, I think that the moment you say that you restrict your query complexity, it's just as in the standard property testing, then you have to give some relaxation. It sounds as a natural relaxation to me, but one could argue that one can put a different, people have studied, for example, edit distance in the standard model. You can also compose the Earth mover distance with the Earth with the edit distance in this model, and there would be a different model. But I think that really you don't want to measure it just by the total variation distance, because this will force you to read the entire sample.
Okay, thank you, Oded. So we will move to the next talk, and it's by Haike, and please share your slides.
Hello, can you see the screen?
Yes.
Okay. Hello everyone. I'm Haike from Tsinghua University. Today I'm going to introduce our work, Embeddings and Labeling Schemes for A*. This is a joint work with Talya, Iden, and Piotr Indyk from MIT. A* is a classical and popular algorithm for pathfinding and has been used in many fields like robotics and game solving since 1960s. Although A* has good empirical performance, there are few studies on its running time analysis. A* search uses a heuristic function to estimate the distance from one vertex to the destination. The quality of this heuristic function directly determines the performance of A*. Traditionally, the heuristics are chosen by human experts based on the properties of the underlying problem. Recently, there is a trend to use machine learning to automatically learn the heuristics. Our paper wants to study the potential of these learned heuristics. We try to understand the relationships between the heuristic function and A*'s running time. First, before starting our analysis, we need to formalize the procedure of A* algorithm and some properties of A*. Please see the pseudocode on this page. A* starts with a set capital S equals S, which is the south vertex S. At each time A* expands a vertex U according to this rule, it will select the vertex with the minimum estimated distance calculated by the du plus hut. Here du is the distance from S to U, and hut is the estimated distance from U to the destination T, and this is provided by the heuristic function h. And then this new vertex U will be added to the set capital S and use this to do the iteration and update the distance to other vertices in this loop. This while loop process will end when the destination T is added to the set capital S. So here is a toy example for A* algorithm. In this graph, we want to query the distance from A to F, and the black numbers here on the edge are edge weights, and the blue numbers above each vertex are the estimated distance lower bound from itself to the destination provided by our heuristic function h. Initially, at round 0, the capital S equals to A, which is only the starting point. And in round 1, the next to be scanned is B, because 1 plus 1 equals 2, which is the smallest among all the other vertices. And the next to be scanned is C, according to the rule on the last page. And then E will be scanned, and finally F will be scanned by A*. In this page, we will briefly introduce two propositions for our later analysis. They are consistent heuristics and scan condition. According to Hart et al. 1968, consistent heuristics guarantee that when A* stop condition is met, which is when the destination is added to the set capital S, the shortest path must have already been found, thus ensuring A*'s correctness to find exactly the shortest path. And in our paper, we will only consider the performance for those consistent heuristics. If A* use consistent heuristics, and then we have the scan condition also provided by Hart et al. It says that one vertex U here will be scanned by A*, or in other words, will be added to the set capital S before T is added to the set. If the distance from S to U, DSU plus HUT is smaller than the distance from S to T. When this is an inequality, but when this inequality becomes an equality, whether you will be scanned is a little bit tricky and will depend on the tie-breaking rule. We omit the tie-breaking here for simplicity, so you can refer to our paper to see how we cope with the tie-breaking here. The metric in our paper we consider are called additive overheads on average. Please see our definition 1.1. Before giving the formula, we will give two notations first. The first notation is PST, which denotes the vertices on the shortest path between the starting point and the destination. And capital SHST is the vertices scanned by our A*, given the starting point, the ending point, and the heuristic function h. This is a toy example on the last page. And in this graph, PAF equals ACEF, which is the shortest path between A to F. And the second set has an additional vertex B, because B is scanned by A star, but not on the shortest path. We say that heuristic H has additive overhead C on average if for randomly chosen pair of vertices, A star scans at most C additional vertices than the minimum possible number of vertices. Note that our metric only takes into account the size of this set S, but not the time spent by the whole algorithm, and it can be seen as a property of the heuristic function and the graph. The main heuristic types we consider for our paper and A star are norm-heuristic and labeling heuristic. We think that their generality can cover most of the commonly used heuristic functions. We first say definition 1.3. For norm-heuristics, this is its expression. We first design a mapping pi projecting each vertex to a vector in a high-dimensional space with dimension d. And then we use the LP norm in the embedded space to calculate the estimated distance between two vertex. And then in definition 1.4 is our called a labeling heuristic. For labeling heuristics, first we also design a function f projecting each vertex to a high-dimensional vector with length L. And then we use a mapping G, map a pair of vectors to a length, estimated distance, lower bound. The difference here is that compared with norm heuristics, labeling heuristics supports arbitrarily the function G, but not need to be the LP norm. However, we require that the value in each dimension must be a value taken from 0 to C, so it has a limited precision. And for norm heuristics, we does not have this requirement for the high dimensional vector. This is our table result, and in the remaining of our presentation, I will elaborate on this table. So there are many results, and we first look at this one. We first look at theorem 1.6, the lower bound result for LP norm heuristics. Our theorem says that we can construct a n-vertex graph if the embedding dimension d is smaller than n over log n. Here, then A star will scan omega n number of vertices. We can construct such a hard instance to let A star suffer from this high complexity. Here LP norm heuristic covers the common used Manhattan norm and Euclidean norm. And this result says that in our instance, A star's performance is no better than the trivial Dijkstra. We next will talk about theorem 1.7 on the lower bound for L infinity norm heuristics. Our result says that we can construct a weighted n-vertex graph whose maximum shortest path consists of constant number of hops, such as if A star heuristics use L infinity norm in an embedded space of dimension d smaller than n to the power of alpha, then A star will scan at least n to the power of 1 minus alpha vertices on average. Here alpha is an arbitrary parameter to be set between 0 and 1. Additionally, our constructed instance for this lower bound theorem can be transformed into a grid graph if alpha is smaller than 0.5. And this is the result for theorem 3.4 here. Next, we talk about theorem 1.8, the lower bound result for labeling heuristics. The result for labeling heuristics achieves almost the same trade-off here, n to the power of alpha versus n to the power of 1 minus alpha compared with the previous one. So we can skip the statement here. Although they have almost the same trade-off, but they use different proof strategy. In the second part,
1 more minute.
Then we talk about our upper bound results. We will only present the stronger version, theorem 1.12. Theorem 1.12 says that assuming the uniqueness of shortest path, we can construct a consistent labeling heuristic of length n to the power of alpha, enjoying an average overhead n to the power of 1 minus alpha. So this is matching upper bound and upper bound compared with the previous theorem. So this is our table. In conclusion, we theoretically studied the performance of A-star algorithm by analyzing the relationship between the complexity of heuristic function and the number of vertices scanned. For norm-heuristics and labeling heuristic covering the most commonly used type of heuristics, we provide matching lower bound and upper bound results. And our results can also be potentially used in the real case because they can be transformed into grid graphs. And that's all. Thank you.
Thank you very much. Okay, so also round of applause, which we don't get that much in the Zoom conferences. Okay, so any question? Okay, so I think our next speaker is Iden.
Yes, I'll share my screen.
Sure. So I will let you know when you have one minute left.
Okay, thank you.
Okay, thank you.
So can you see my screen in like full?
Yes.
Okay, great. So hi everyone, I'm Iden, and today I'll talk about our work on sublinear-time computation in the presence of online erasures. This is joint work with Sofya at Boston University and Nithin, Varma, Chennai Mathematical Institute. In this work, we initiate the study of sublinear-time algorithms that compute in the presence of an online adversary. A sublinear-time algorithm is a randomized algorithm that has query access to some very large data set via an oracle. We represent the data set via a function f, and the algorithm is supposed to output some approximate answer about the function after making a subliminal number of queries in the size of the input function. The adversarial model we consider is the following. After answering each query to the data set, the oracle or the adversary can hide a small number of entries. Sorry, I see something in the chat. Oh. Okay. So the adversarial model, which we call the online erasures model, is parameterized by a natural number t. After answering each query of the algorithm, the oracle can erase up to t entries from the input function. I'll demonstrate this model for the case when t is equal to 1. At the beginning of the runtime of the algorithm, all the entries of the function are non-erased. Suppose the algorithm's first query is entry 2. Then the oracle first has to answer this query by returning f of 2. Then the oracle can erase one entry from the function. Suppose it chooses to erase entry 3. Then the value f of 3 will be hidden from the algorithm for the remainder of its running time. If the algorithm at some point queries entry 3, then it will receive a special erasure symbol. And this process is repeated for every query of the algorithm. Here are some motivating scenarios that we consider for this model. The first scenario considers the case of individuals who request that their data be removed from a data set. Particular such requests can be adaptive to the queries of the algorithm, as individuals can be prompted to restrict access to their data after noticing an inquiry into their or others' data. Another scenario is that of a legal setting when an organization is served a subpoena. The organization is legally bound to first answer this query, but afterwards they can destroy related evidence that was not involved in the subpoena. The tasks we consider in this model in this work are standard property testing tasks, which is a subset of sublinear-time algorithms. Property testing was first introduced by Rubinfeld-Sudan and Goldreich on. In this case, the sublinear algorithm is parameterized, is given value epsilon between 0 and 1. And its goal is to accept if the function f has some specified property and reject with high probability if the function is far from the property, where the distance is measured by this parameter epsilon. And by epsilon far, we mean that the function must be modified in at least epsilon fraction of its domain to have the property. And we also want the tester to make a sublinear number of queries in the size of the input function. We consider property testing in the case where access to the function is via the adversarial oracle that I just described. Then the goal of an epsilon online erasure resilient tester is the same as that of a standard tester. It's supposed to accept if the function has the property and reject with high probability if the function is epsilon far from the property. We show the following results. Some properties of function can be tested in our model with the same query complexity as in the standard model. Namely, these properties are linearity and quadraticity. And here we're comparing query complexity for a constant erasure budget T. Then for linearity, we show matching upper and lower bounds in terms of the erasure budget T. On the other hand, we show that some properties are impossible to test in our model, even for T equals to 1. One such property is sortiness of arrays. And the key takeaway from this result is that the structure of violations to the property play an important role in determining testability of the property within our model. So in the rest of the talk, I'll just give some high-level overview of our results on linearity testing. We consider functions which are Boolean valued and whose domain is the d-dimensional hypercube. Such a function is linear if it can be expressed as a sum of input bits for some subset of the bits. Equivalently, it can be shown that such a function is linear if f of x plus f of y is equal to f of x plus y for all points x and y in the domain. Linearity testing has been, in the standard model, has been widely studied due to its connections with probabilistically checkable proofs and hardness of approximation results. In the standard model, it can be tested with 1 over epsilon queries. The tester was introduced by Blum, Luby, and Rubinfeld, and then the analysis was tightened by Bellar, Coppersmith, Kiwi, and Sudan. In our model of online erasures, we show that linearity can be done with log t over epsilon queries. Recall that t is the erasure budget that is given to the adversary. And we also show a lower bound of log t for the query complexity. The tester of Blum, Luby, and Rubinfeld is very simple. It repeats the following procedure. It samples 2 points x and y uniformly at random from the domain. Then it queries the values f of x, f of y, and f of x plus y. And it rejects if f of x plus f of y does not equal f of x plus y, since this cannot happen for a linear function. In this case, we say that the pair xy violates linearity. Then the analysis of the tester depends on this key structural theorem of Bellar et al., which says that if a function is epsilon far from linear, then an epsilon fraction of the pairs x and y in the domain will violate linearity. It's not too hard to see that the online erasures will break the BLR tester. If the algorithm queries 2 points x and y, and it might receive their values f of x and f of y, but afterwards the oracle will erase the value of f at x plus y. And so if the function is far from linear, then the tester would never be able to see a violation to linearity. So we need to consider a new linearity tester. And to analyze this tester, we also come up with a new structural theorem, which generalizes the previous theorem of Bellar et al. This theorem says that if a function is epsilon far from linear, then for all even k, an epsilon fraction of the k tuples x1, x2 up through xk violate linearity. By which we mean that the sum of the values f of x1 plus f of x2 up to f of xk does not equal the value of f at the sum x1 plus x2 up to xk. And the proof is also via Fourier analysis, and it generalizes the proof of Bellar et al. In the next slide, I'll give you like a high-level description of the algorithm, and you'll see how the structural theorem plays an important role in this algorithm. So the algorithm is as follows. It first queries a reserve of log t over epsilon points that are sampled IID from the domain. Recall that t is erasures per query. So suppose it queries this like 4 points to begin with. Then the adversary can erase linear combinations of these points. So the edges here represent sums of points. Then the tester repeats the following 1 over epsilon times. It samples an even number of points from the reserve, and it queries their sum. So if the tester is lucky in this case, it will query either like the sum of x1, x4, or the sum of all 4 points, which has not been erased by the oracle. Then the tester checks if this tuple and its sum violates linearity, and rejects if the tuple is violated. And if it finds no violation after repeating this checks, it will then accept. Okay, so that describes our results on linearity testing. So I'll conclude with some open questions. So as I said, in this model, we can test whether a function is a polynomial of degree at most 1 and a polynomial of degree at most 2, which is linearity and quadraticity. But is it possible to test in our model whether a function is a polynomial of degree MOSK for any k greater than 2? In the standard model, this is possible with very efficiently with 2 to the k over epsilon queries by a result of Alon et al. The next question concerns the query complexity for testing quadraticity. So for linearity, we show both matching upper or lower bounds in terms of the dependency on T. For quadraticity, we have a tester which is efficient in terms of the dependence on the distance parameter epsilon, but the dependence on T is doubly exponential. So the question is, what is the query complexity in terms of T? Another question is about the comparison between our model and another erasure model introduced by Dikshe, Raskhodnikova, Takurta, and Varma, in which the erasures to the function are done before the algorithm makes any of its queries. And for this reason, we refer to that model as the model of offline erasures. The two models are not directly comparable because erasures are budgeted differently. We show that sortiness is impossible to test in our model, but it's very easily testable in the model of offline erasures. So the question is whether there's a property for which the inverse holds. It has smaller query complexity in the online model than in the offline model. Finally, it'd be interesting to study other sublinear tasks in this model. So we only study property testing tasks, but the model of online erasures is defined more generally to work for any sublinear task. Such examples of interesting tasks would be estimating parameters of graphs or functions. So that's it for our talk. Thank you. I heard the alarm.
You precisely finished. I am not sure who is going to speak for the next paper, but let us know in the chat if you don't have the panelist privileges, or if you have, just share your slides.
Should I stop the share?
Yeah, thank you. Oh, by the way, you have time for a question from Iden. If you have question.
What's our empirical example of the application via model?
Yeah, so one example we consider is, for example, if you're running an algorithm, but individuals request that their data be removed from the data set at some point, then you should be able to keep running the algorithm and obtain the desired answer.
I see, thanks.
And there is a question in the chat. How does it compare with the model with online modification instead of erasures?
Yeah, so I'm not sure if the model of online modifications has been defined in any other work, but we did consider it. And some of our results carry over also to online modifications. You can show that basically as long as the algorithm never queries a point that has been erased by the oracle, so as long as this happens with very small probability, then the tester can also work with online modifications. So for example, our linearity result carries over to online modifications, but it definitely needs more investigation.
So one more question. Can you say anything about the error and instead of erasures?
So is error also something like online modifications? That's the same thing?
I honestly, I also didn't.
Yeah.
But if
yeah, it sounds like.
Feel free to elaborate, and I will read that.
It sounds like a similar question to online modifications.
Yeah, maybe.
So. Yeah.
Yeah.
Okay.
Any more questions? Okay, so one more time, I invite the speaker of the first paper on the extension of competitive equilibrium with Chores to please share their slides. Okay, maybe we can move on to the next talk. So you can please share your slide, and I will let you know when you have 1 minute left. Okay.
Sure. Okay.
Thank you.
So, okay. So hi everyone, I'm very happy to be here to talk about my recent work. So let's start from a running example. So we have several restaurants and we have two people, Alice and Bob. They are rating these restaurants and we want to give them proper reward such that they can provide high quality ratings, honest ratings. And in such case, we cannot use flat payment because they can just provide garbage but get our payment. And also we cannot check their answer because they are just subjective answer. There is no ground truth. And the third traditional reward system is like, maybe we can pay them according to their agreements. But in such case, first, even they are honest, they can have very different tastes. And also if we only pay them for the agreements, they can just give all the restaurants the same score, like the highest rating. And in such case, there is no information, but they can get all the payments. So let me introduce one paradigm in my previous work with my collaborator. So this is like, we just think their ratings for the restaurants are IED samples. So we just think there are like infinite number of restaurants. So basically infinite number of IED samples for some joint random variables. And then we can just estimate the joint distribution perfectly. And this joint distribution just represents, for example, it's like for a random restaurant, what is the probability they both like it? What is the probability they both dislike, or one like, one dislike, something like that. And after we get the joint distribution, we can just like calculate the mutual information based on this joint distribution. And intuitively, in such case, like no matter they are like positively correlated or negatively correlated, the mutual information is high. And we're gonna use this mutual information as their payment. And the reason we want to use mutual information is just because this data processing inequality. So at a high level, it's just like if one of them like perform the strategy, they're gonna like perform like processor, their ratings, it will decrease their payments. And mathematically, it's just like they perform a strategy, like they just multiplying some transition matrix on the joint distribution, and the mutual information decrease, and we pay them by the mutual information, so their payment decrease. In such case, they don't want to perform some strategy on their ratings. So that is what we want. We want them to provide their honest original ratings. Okay. And I think you already noticed that the problem here is like, we just need infinite number of like restaurants. They just need to rate infinite number because we want some like perfect estimation of the joint distribution. And in practice, they may only rate 10 restaurants. We only assign them 10 tasks. In such case, we only get the frequency matrix, like how many restaurants they both like, something like that. And even we assume that they only care about their expected payments. In such case, we can just construct unbiased estimator, but like the Shannon mutual information, there is like log there. We cannot use some finite number of samples to construct. So that is my previous work. So this called the determinant-based mutual information. So this very simple, it's just defined as a determinant of the joint distribution matrix. And I put the absolute value there to make sure it's non-negative. And I can also put square there, it doesn't matter. And it satisfies data processing equality. I won't go into detail. And the most important thing here is it has this polynomial format. The determinant, it has polynomial format. In such case, we can have unbiased estimator with only a finite number of samples. And in like this 2x2 case, we just only just like square, we just only need 4 restaurants, 4 tasks there. And because of that, we can just like use these 4 restaurants to construct the unbiased estimator of this mutual information and use this unbiased estimator to pay them. And because it satisfies data processing equality, so it's fine. So the whole point here is that we want a mutual information measure. So, okay, so this is the question this paper wants to address. Is any more mutual information like that? In such case, we can construct more reward system, have this property. And this actually, this mutual information thing reduce this question to this information measure design. So we want the mutual information satisfy first data processing equality, second it should has polynomial format. So this is the 2 property. And this is the only intellectual slide here. I think also the only intellectual idea in this paper. And maybe in appropriate time you want to use this. It's like if clever is something satisfy partial order. So if I'm less clever than you and someone is less clever than me and like she or he also less clever than you, if satisfy partial order, and we want to create a mountain function on this partial order. So basically we want to measure how clever you are, and we want this measure satisfy mountaicity. And one natural idea is that we can just count the number of people that are less clever than you, right? Because if I'm less clever than you, and then the people who are less clever than me gonna be less clever than you as well. And in such case, the number of people who are less clever than me gonna be less than the number of people who are less clever than you. Maybe it's improper, but it's just an idea here. And that comes to this idea, this volume mutual information. So I'm going to measure how informative this joint distribution is by measuring the volume of the space of the joint distributions that are less informative than the original joint. So I see less informative, it's just like this data processing, it like has some transition matrix multiplying on the left. And it's easy to prove it satisfies partial order. And that is the idea of this, is the same idea of this clever thing. And the point is, if I define use this volume, I can just use any measure, like any density, as long as it's non-negative to measure the volume. And if this density is uniform density, we can actually get something proportional to the determinant mutual information. And if this density is polynomial, and then it's polynomial. So by definition, this mutual information satisfies data processing equality, because data processing equality essentially is a mountain function regarding to the partial order. And I just defined it this way. So it by definition satisfies data processing equality. And also by properly choosing the density function as polynomial, we can also make it as a polynomial. And remember, what we need is something satisfy data processing equality and also has polynomial format. Once we get this, we can get unbiased estimator with finite number of samples, which means finite number of restaurants, and we can get the reward system we like. And that's the whole point. And I think others are just like, this picture is just showing that what is like how we tune this property of the density, and we can just get this new mutual information. And I just submit there. So the whole point of this paper actually is just that new mutual information family satisfy data processing equality and being polynomial. And because of that, we can use that to construct a new family of reward systems and satisfy this strategy proof defined this way because of data processing equality. And also, we only need the participants to rate a finite number of tasks, because we can use that to construct unbiased estimator. And other properties, you can like read the paper for more details. And I think that's all. Yeah.
Thank you very much.
Thanks.
Any question for you, King? Okay, so if there are any speaker from the paper on the extension of competitive equilibrium with Chores, please let us know now.
Yeah, I guess given the time constraints and another session starting in room B, it's not practical if you haven't heard from them. I guess there is a video and eventually we'll hear back from them.
Okay, yeah, so there is a video in the schedule and we can watch it all there. So thanks again for the speakers who gave the talk in this session and also the attendance. Thank you very much, and we'll see you in the next session.
Thank you.
Bye-bye.
Thank you, Maryam.
Bye-bye.
Thank you.